Have you ever stopped to think about that invisible world just humming with activity right there on your desk? I mean, every single time you print a document or you grab a file off a shared drive, your devices are having this rapid-fire conversation. Well, today we're going to decode that language. We're telling the story of Ethernet, the protocol that makes our whole modern digital life possible, one message at a time. So let's get started.
You know, it seems so simple, right? You just click print, and a few seconds later, your document just magically appears. But underneath that simple action, there's this incredible hidden journey happening. Your data has to navigate a really crowded digital highway, and it's following a super strict set of rules to avoid a total traffic jam. So let's follow one of those messages and see exactly how it avoids all that chaos.
To really get how modern Ethernet works, we've got to go back to the beginning. Imagine your entire office network was like an old-school telephone party line, where everyone was hooked up to the same single wire and could hear everybody else's conversation. Yeah, kind of chaotic.
So this early design was called a bus topology, and it had one really huge consequence. When one computer sent out a message, it was like it was shouting in a library. Every single device, your PC, the one next to you, the server, they all heard that message. Now, it was super easy to set up, but man, it created a very, very noisy problem.
And that, right there, is the heart of the challenge. On a shared line, if two devices try to send data at the exact same moment, their signals literally crash into each other, and it all just becomes a garbled, completely useless mess. So the first and most critical problem Ethernet had to solve was this: how do you manage the conversation?
The solution they came up with was honestly brilliant in its simplicity. Ethernet's creators developed a set of rules. You could think of it as a kind of digital etiquette to make sure devices behave politely and didn't just talk over each other. It's called CSMA/CD, and it's really all about listening before you speak.
Okay, let's break that down, because it sounds complicated, but it's not. First, carrier sense. That just means you listen to the line to see if anyone else is talking. Then you have multiple access. That's just a reminder that everyone's on that same line. And finally, the most important part, collision detection. This is the emergency plan. It's what happens when two devices, inevitably, speak at the same time.
So, it all boils down to this four-step dance. It's actually pretty clever. First, your computer listens for silence on the network. If it's quiet, great, it starts sending. But oops, another computer had the exact same idea at the exact same time. A collision happens. Immediately, both devices send out a jam signal to make sure everybody on the network knows the line is clogged up. And then, this is the key, both devices wait a random amount of time before they try to send again. That randomness is what prevents them from just colliding over and over.
Okay, so our devices now know when it's okay to talk. But on that noisy party line, how does a message know where it's supposed to go? I mean, if every device hears every single message, how does your printer know that this specific print job is meant for it and not for the PC right next door?
Well, the answer is a unique address. Every single message, which is called an Ethernet frame, has a destination address baked right into it. As that frame zips down the wire, each device takes a look at it and asks a simple question. Hey, is this for me? And only the device whose address matches the one in the frame will actually grab it and process it. Everyone else, they just ignore it.
And this unique identifier is the MAC address. The best way to think of it is as a digital fingerprint for your device's network hardware, and it's permanently assigned right at the factory. The first half of the address is like a code for the manufacturer, telling you if it was made by Cisco or Intel. The second half is a unique serial number. And the result of all that is that no two devices on the entire planet should ever have the same MAC address.
Now, it's really easy to get MAC addresses and IP addresses mixed up. So here's the best way to think about it. A MAC address is like the permanent, unchangeable serial number that's stamped right onto your device. An IP address, on the other hand, is more like the mailing address for the building you happen to be in right now. The MAC address is for talking to people inside your own local network, inside your building, while the IP address is what gets the mail delivered between different buildings or different networks.
So we've got rules for talking and we've got unique addresses. But that old party line itself was still a huge problem. As more and more devices joined, the line just got noisier, collisions happened all the time, and the whole network slowed down to a crawl. The system needed a serious hardware upgrade. It needed to go from being a dumb megaphone to a really intelligent switchboard. And this right here is one of the biggest leaps forward in Ethernet's history. On the left, you've got a hub. A hub is,
Well, it's dumb. It's basically just a megaphone. When a message comes in on one port, it just shouts it out to every single other port, creating one massive collision zone. But on the right, we have a switch. A switch is smart. It's like a telephone switchboard operator. It learns exactly which device is on which port and creates a direct private line between the sender and the receiver.
The difference in performance is just night and day. With a hub, everything grinds to a halt as you add more devices. But a switch, it creates a private little line for each conversation. Every single port is its own collision-free zone. This means dozens of devices can have simultaneous, full-speed conversations without bothering each other at all. This was the massive upgrade that really made modern office networks possible.
So how does the switch pull off this magic? It learns. When a device sends its very first message, the switch looks at the source MAC address and it makes a little note. Okay, MAC address OA is on port 1. It builds this table, mapping every MAC address to a specific port. So the next time a message comes in that's for OA, the switch doesn't shout it out to everyone. Nope. It just looks at its table and sends it directly and only to port 1.
So we have just one last piece of the puzzle to solve. Your computer knows the building's mailing address, that's the IP, but to actually deliver the package, it needs the specific apartment number, the MAC address. So how does it get it?
This is the exact problem your computer is facing. It might know it needs to talk to the printer at IP address 192.168.1.100, but to actually build the Ethernet frame for that local delivery, it has to have that printer's unique MAC address. The solution is a process called ARP, which stands for Address Resolution Protocol. And it's just beautifully simple. The computer basically shouts out a broadcast message to everyone on the local network, and it says, "Hey, who has the IP address 192.168.1.100? Every device hears it, but only the printer recognizes its own IP. The printer then replies directly to the computer saying, "Hey, that's me, and here's my MAC address." The computer then smartly stores this little IP to MAC pairing in a local table. It's called its ARP cache. That way, it doesn't have to go around shouting the same question over and over again. And just like that, our message is ready to go. It knows its destination's local MAC address, thanks to ARP. It's being sent through a smart switch that's going to create a direct path. And it has a whole set of rules to follow to make sure there are no collisions. The journey from your computer to the printer is finally complete.
So what we've seen is how Ethernet brilliantly solves the problem of local communication. It gives us the addresses, the rules, and the hardware for devices in the same building to talk to each other super efficiently. But what happens when that message needs to leave the building and travel to a different network, maybe halfway around the globe? Well, that's where IP addresses and routing come into play. And that is a story for another explainer.